All right, part 3 of chapter 15. We have the Laplace transforms, developed all of those properties and so forth. Now we need to turn to getting back from a Laplace transform back to what? The time domain. So let's just say here's a Laplace transform. We're just declaring one. We don't know what it is. Doesn't matter. I want to just mention here, this is not necessarily a transfer function. Okay? It's a function of s, but the Laplace is not necessarily equal to the transfer function. So I just want that distinction before we get too far along here. You may recall from back when the Laplace was introduced in the early part of chapter 15, the reverse or the inverse was mentioned, that it's an important companion piece. I pointed out here only to say that it was brought up before. Notice it relates the f of s to the f of t, back to the original function that we, converted that way. I just take one look at this math with these bounds, and this may or may not get messy, but it's enough to say if I can avoid that, I'd really kind of like to. All right, so how do we find the inverse Laplace and try not to get that messy? Okay, first step, use partial fraction expansion to decompose the fs into simple terms. So brought up another one of those old algebraic or calculus ideas, the partial fraction expansion. Okay, so if you haven't, you'll be refreshed on these. I told you there's going to be a few concepts like this that we'll have to dig up. Here was one. I just grabbed this from the wiki library. So partial fraction expansion, of course, is not limited to what we're doing here. So here it is as the ratio of two polynomials in the same variable, x. In our case, what? These will become s's, right? These will become s's. And it can be decomposed into the sum of a bunch of fractional parts with constants up above, constants in the numerator. This is a really powerful tool. You may recall it, like I say, from algebra or calculus. Once we have that, you can almost guess where this is going then. These look kind of easy, right? Here was the work. Now all I got to do is look them up in a table, right? So here is that table from earlier. You have, right, this relating, whoops, f of t and f of s, right? It's this process right here, tabulated, whoops. Where am I at? This process right here, all tabulated. Can't find my marker. So we like that, and we hope we can stay up toward the top of the table with the easier ones, but it doesn't matter if we have to get down below. But you see how these, this was maybe pointed out earlier with when we were doing Laplace transforms, but how these all just kind of, move like this. Nice things over simple powers. All right. So what we're going to try to do with partial fraction expansion, obviously, is create these simple terms, something over something, and the sum of a bunch of those. We would like to do that a lot. Three important cases, kind of the reverse of what we had going before. Simple poles. That's, of course, going to be the easiest because we're going to get poles isolated in each of the fractional terms. Repeated poles, where the poles, you'll see if you were to put it together, the square, s will occur in a squared form. And then complex poles, where you actually have something that's off the real axis and up in the imaginary, the real imaginary plane. Okay, so let's take the simple poles first. This is what it would look like. We've got our f of s is ns, over ds, right? Only now the book has written the ds as this product of poles. Notice the powers here are all 1, right? That would make them simple. So that would imply, or it means, if they're simple, none of the pi's are equal to any of the others, right? So all of the pi's have to be different from others. So let's take a little bit closer look. So for fs, it's important that to do partial fraction expansion, the degree of the numerator is less than the degree of the denominator. Now, why is that? Well, you can see if I am to multiply out, so this is where I'm heading, and now I've put it in terms of our exact case here. But if the degree of the denominator is less than or equal to the degree of the numerator, if I were to try to recombine this, in other words, instead of expanding, I were to put it back together, I would end up with a power here I must end up with a power that's less than the power of the numerator. That's just, right? If I cross-multiply all these terms, the numerator will end up less than, the terms of the numerator will end up less than the degree of the denominator. If that isn't the case, I'm not going to be able to do partial fraction expansion. Okay? So that's one thing. Now, we have to say here that so I can summarize that. All the pi's have to be not equal to any other, right? Now I'm going to find the k's, right? How do I find the k's? I'm going to find the k's by factoring out each s plus pi. Okay? So how do I do that? Here's how I do that here. Here I have factored out s plus pi, and if I do that out of the first term, right, what happens? If I take the first term here and I factor this out, right, what I'm left with is k1. Okay? If I were to multiply back or divide back through by s plus pi, I would get exactly back to this term. But now each of the other terms have to be multiplied by s plus pi, because I multiplied everything through by that. I multiplied the left-hand side and multiplied each of the terms here by s plus pi, same as factoring. Okay, so now I have isolated the k1, right? You can guess where this is going. The next thing I'm going to do is repeat the process. There's a simple way to say it. That yields k1. And why does that yield only k1? Well, once I get that, I've isolated it, and I can simply plug in minus p1, or in this case minus pi, and what will happen here? All of these terms, okay, this term at s equals minus p1, this term becomes 0, as do all the others, right? When I plug in minus p1, and that would just leave me with k1. So that's what I mean by isolating. You're going to separate them out, and the general process will be this. You just keep doing it over and over and over again. Or you could just say, by the way, there's no particular order to the k's, k1, k2, k3. You could take them in any order because they've all been broken out as independent fractional components in the sum of fractions. Okay? Now, what's good about this? I go back to my table and I find out, 1 over s plus a, this guy, corresponds to this guy, right? This is f of t from the table. this is f of s for that one term, right? So imagine now, how am I going to put the whole thing together, my complete f of t, since I broke it up as the sum of a bunch of fractional components, right? Once I did that, I then am going to have those constants, whoops, the constants right here and here and here, times the exponent, whoops, times the exponent of that term. Everyone the same, okay? So, point here is, again, simple poles. Yeah, we like that. Okay. The next one was repeated poles, right? So now we can take our identical approach of partial fraction expansion and say, now we've got the same pole, right? So notice here, I had a bunch, right? I've got a bunch of these. Whoa. Right? And notice how K1 is the simple pole. K2 is the square of that, out to Kn, which is s plus p to the nth. Okay, and you'll have to do this kind of expansion for each distinct pole. Now, what do I mean by that? Well, there might have been a bunch of poles. I'm just talking here about how do I manage the repeated ones. And you can see there's a part here left over that I haven't dealt with, right? Because I'm comfortable knowing that the Laplace transform, this guy, of the whole ns over ds, n of s over d of s, the whole thing can be composed of these repeated ones here, again, where I've said this, plus whatever's left over. And this is the part that has no pole at P. Okay? We'll deal with that one later, in the same way. So what are we doing then? We take out the k to the nth term. Big surprise, same process. We factor out this to the nth. Okay? By plugging in at minus p. So we're going to take this guy out, right? Then we'll go back and take the derivative of that and evaluate that at minus p, right? So we're going to get, we're actually going to get an f of s for that. And we're going to factor out each of these. Now we're going to differentiate this and keep doing that. Now, so a couple of things to note here, right? Every time you differentiate, whoops, where am I? Every time you differentiate, pay attention to this. It's a factorial going on here, right? Because you're going to accumulate terms. So it's going to be to that level. And at the end, you're back here again with this factorial to the power of the derivative that you're taking. Okay? Pile them up. Now, what's going on per term? All right? So per term, if I take the inverse Laplace of 1 over, right, here's the term. What am I going to do? I'm going back to my table and look this up, and this is the term that I get, right? So I'm going to do that for every term in the repeated pole section. So I'll do it for that, I'll do it for that, I'll do it for that, I'll do it for that. This whole part with no pole at minus p is going to have to be dealt with separately. But again, the beautiful thing is we now have partial fractions. So this is a summation. So all I'm going to do is go get all my terms with reducing values of n. Okay, and when I do that, I will have something like this. So here we can see it. Let's first identify all this stuff. We've carefully saved all of this. Right, there it is. We got all of this out here, and we've just tossed him in and saying, oh, well, that's f1 of t when I get around to finding out what that is. Right, I may have to do the inverse Laplace on some other portion of this. And now each of the terms, right, here they are. Here's term 1, term 2, term 3, right, going on. Okay, let's take a look at each one. Once they're decomposed, I know I've got something of this form, right? So here that is applied to this. I've got my t to the n minus 1. Well, when n is 1, t to the 0 is 1. Over 0 factorial. Good thing 0 factorial is 1 and not something else. E to the minus at, well, in our case, a is p, the pole location. Okay, here it is applied again to 2, only now I've got 2 minus 1, so t has a 1, and 2 minus 1 factorial is 2. Now here, at 3, you start to see this factor shows up as not 1. The first two you get away with easy because 0 factorial is 1 and 1 factorial is 1. So you can sort of forget that it's there, but it's there and the pieces are all there. So you can see for repeated poles, the same good deal applied to us. All right, so let's go on now to complex poles and see what we have there. So these are poles that have orders greater than 1. And they're complex. It's not so much the order that's at issue here. We had that already. But we're going to look at complex poles. Here's the general form that we want to talk about. Okay. We're back once again separating, right? So we should be used to this by now. This is the part we can't deal with. Okay, this pole is not our current pole. Right? So we're going to do partial fraction expansion, but we're going to do something else here that needs to be done. We're going to have to try to make the ds, the denominator, look like this. Okay? And this, of course, is called completing the square. Whoop. Complete the square. All right? We're going to want to do that. So how do we do that? Let's start by, all I've done here is copy this, is now down here, right? We're going to walk through steps. We have s squared plus as plus b. Now we can sort of sense from this the completing the square opportunity because we've got the squared term plus the power of 1 to the degree 1 term plus a constant. Okay, and if we mess around enough, but with alphas and betas like this and this, we can get it around to something that's going to be a square. So here's the suggestion: s squared plus 2as plus alpha s plus alpha squared. Right? This thing is what we like. This is a square of something. In fact, it's right the s plus alpha squared. Right? This is that. And the leftover is beta squared. So we don't know whether that's a nice number or a crummy number or whatever, but it is a constant. Okay. Now let's let this, right? So we're going to let our numerator, the key portion of it, take on this same shape. Well, what's important about the same shape? Wow, here's our pole occurring there. We've got an s plus alpha. Okay, so why did we do this? Because we wanted to anticipate trouble in the numerator. So here's our s plus alpha, and then here's our beta for any constant that's needed. All right, so when we let that happen, let's go through with the whole thing. We've now set up something where fs, we're back to separating, separating our pieces. This is a simple separation, right? The first portion goes over here. This portion goes over here. No problem. This is just hanging on. Hang on for later. Okay? That's what's going on there. We don't want to lose it. Now, one thing we might begin to recognize here is I've got beta sitting up here, beta squared down here, and this down here. This is some constant. Okay? So this whole term, remember the next step is going to be look it up in the table. This is good. This has the form without the B1, but it has the form, we'll put that out front, of what? The sine. Remember the sine in the table is what? It's omega over s squared plus omega squared. Well, we sort of have that look here. If omega is equal to beta, right, and s squared is actually equal to s plus alpha squared. Boy, we're pretty close. So that omega over s squared plus omega squared, right, we recognize that as the sine of beta t. Okay? And all we have to do is account for this alpha business, and we know now, because of also from the tables, that that's going to be a displacement, so we'll have an e to the minus alpha t factor. Let's go back over here and kind of anticipate what's happening. Here we've got s plus alpha squared. Oh boy, this looks like some form of s over s squared plus omega squared. Wow, and that's looking like a cosine, right? Cosine of omega t. So it's going to be in the same genre as this. And indeed, that's what all this stuff is going to give. Here we are. Here's our constants, A1 and B1. Here's our frequency that we extracted out. And then here's the shift. Okay, the offset. Really good. So let me sum up. Just sort of extracted this from the text, so you can find it there, just not laid out like this. No matter what pole types, there's two general approaches. The one that we really spent all our time on, where is it here, was this one, the method of algebra, where we set this equal to partial fraction expansion, an ns over ds, did an expansion and separated out the k's, multiplied the result by the common denominator to isolate the k's, and then solve for the k's by equating like powers. Remember? And we could leave that part that doesn't fit, the f1 of s, like we did in complex and in repeated poles. All right, substitution of values they refer to in the text if you can find some convenient values of S to form a set of equations. Okay, and convenient is something you'd want to get familiar with, probably with practice. But you're going to want to form a set of simultaneous equations and then solve for coefficients that way. All right, so I think we'll move on to trying some problems. Okay, so practice problems. Just going to do bunch of inverse transforms. Lots of great examples in this section. At the end of this section, I'll do practice problems, and then you'll have quite a bit to work with. So here's 15.8. You see it. Find the inverse Laplace transform. In other words, get back to the function of time. Okay, so really this is already broken up into the constituent parts, right? So all we need to do is go, okay. All we need to do is go look these up, look up the terms in table 15.2, right? And you can refer back to that, but it's pretty straightforward. F of t, then, so 5 is just the delta function, right? So it's 5 delta of t, right? And you remember what that is. That's just an infinitely, I don't know about tall, but a magnitude 5, but 0 time, just occurs at some point in time. Plus, now we've got this term, this s plus 4. So we can say this is, we know the multiplier is that, so this is e to the minus 4t. Again, just from the equation. All right, let's look at this guy. We'll take this bottom and turn this into, what can we do? Oh, I know what this is. This is s squared plus 5 squared. So if we take out the s and say it's 7, in other words, just reposture it a little bit, we've got minus 7, and s over s squared plus 5 is minus 7 cosine 5t. Okay, and these last two here, actually, as we've been doing, turn on with the unit step function. All right, so that's that one, and that is the answer. Okay, let's. That one was pretty easy. They'd already done any sense of fractional expansion has already been done. So let's try another one here. And this is a little more interesting. We'll actually get to do the expansion. So I'll start over here on the left, give myself plenty of room. I wonder if I can get rid of this at the bottom. Guess not. All right. So here we are with with the fs given, and we've got. We're going to rewrite this. I'll just work right off of this then. This will be equal to, in our expansion form, k1 over s plus 1 plus k2, pretty lousy k, over s plus 3 plus k3 over s plus 4. Okay, so now what's our rule for these? We have 3 simple poles, right? This is the case of simple poles. There we are. So we're going to take s plus 1 times gs and evaluate that at s equals minus 1. So what does that come to? if we take, that's just our transfer function, or our Laplace transform, 6 times s plus 2. I'll write a lot of this at first. The s plus 1 will be gone. S plus 3 times s plus 4. Okay? And we're going to evaluate that, but we know ahead of time, multiplying by s plus 1, and s plus 1 will end up in the numerator of all of these terms, and this will be k1 plus a whole lot of stuff, all of which will go to 0. Right? So we simply need to plug in and evaluate k1, and that's what? 6 times minus 1 plus 2, 6 times 1, over 3 minus 1 is 2, times 4 minus 1 is 3. So this looks like 1. All right, let's just press on. Same way, s plus 3, g of s at s equals minus 3 is where we'll evaluate. So we've got 6 over s plus, times s plus 2 over now our s plus 1 times s plus 4. Yeah, and that's going to be equal to k2. We know that because things are going to get eliminated. So this is 6 times minus 1 over be equal to minus 3 plus 1 is minus 2 times minus 3 plus 4 is 1. So this looks like 6 divided by 2 is 3. Okay, and the last one, at this point, it pretty much becomes just running with it. The real trick, and we just didn't have much to worry about here, is doing the expansion. In the first problem, we didn't even have to worry about all of that. Where am I at? So this s equals minus 4. And this is going to be equal to k3. We know that. So that'll be 6 times s plus 2 over s plus 1, s plus 3. Right, and if we plug in the numbers, minus 4, 6 times minus 4 plus 2 is minus 2, over minus 4 plus 1 is minus 3, times minus 4, that's another minus 1. So we got a bunch of minus signs, so it looks like this will be equal to minus 4. Huh? Okay, and now if we put the whole thing together, remember, back to this form up here, all we're trying to do is we now have our k1, so we have each of these, right? And we just go pluck these out of the table. F of t is equal to, the first one is 1 e, so that's 1 times e to the minus t, because it's s plus 1. And then we've got a coefficient of 3 and a power of 3. And then we've got a coefficient of minus 4 and a power of 4. Okay? And we can say, because of how this was set up, we can of course say all of this is u of t. Okay? And that's what we've got. Okay. Let's do yet another. 1510. And all right, sometimes I'm not doing the one that's in the text. They changed it because of the text I've got to copy. So here we have, let's just itemize what we've got first. Help set ourselves. We've got 2 simple and 1 repeated. Okay, so we do need to do the fractional expansion. And so that's going to look like this. We know we've got a repeated pole, so let's just put that in. We're going to have to k2 over s plus 1. And I'm whoops, squared, right, plus k1. And I'm doing these anticipating, right, anticipating what the expansion is going to be. So that takes care of the two that are going to result from this, right? This is going to result, two terms. All right, then I have to add k3 over s plus k4 over s plus 3. All right, so we might as well get the dicey ones out of the way first. We know we've got to do the repeated poles. We have to take the s plus 1 squared gs, right? And then we're going to evaluate that at s equals minus 1. So this will give us k2, right, in the whole deal. And if we do that up here, we've got what? S cubed plus 2s plus 6 over s times s plus 3. Okay? And if we plug in all the numbers there, or we plug minus 1 into everything, we're going to get 3 over minus 2, which is minus 1.5. So we've got one of the numbers. Now we've got the unfortunate thing where we have to take the derivative, right? So we have to take the derivative with respect to s, oh, sloppy, of this whole thing, right? Well, I'm just not going to copy all that down. I'm going to take the first derivative of it, evaluated at minus 1. It gets messy enough as it is, as you'll see here. So what is this? This is, go back to gs times s plus 1 squared, right? So we're dropping this out. So we're going to have, to take the derivative, we have the bottom, s times s plus 3. So this is the bottom, times the derivative of the top, which is 3s squared plus 2 minus the top, all right, on the top, times the derivative of the bottom. Now remember, the s plus 1, the quantity squared, is not there, so you really have s squared plus 3s. So the derivative of the bottom is 2s plus 3. Okay, all over the bottom squared, which is s squared times s plus 3 squared. Okay, now the good thing here is we don't actually have to multiply all this out and combine terms and blah, blah, blah. We only need to plug in s equals minus 1. Okay, so here we've got, let's do that as a minus 1 times minus 1 plus 3, which is 2. Let's see, make sure we get this right. Yeah, minus 1 plus 3, which is 2. Sorry, my eyes got sidetracked there. So, and then 3s squared, so s squared is 1 times 3 plus 2 is 5. Okay, minus s cubed, which will be a minus 1, plus whoops, what have I got going on? S squared plus, so here I've got, this is minus 1, this is minus 2, and that's 6. So 6 minus 3, it looks like I've basically got 3 out of that first term. And 2 times minus 1 is minus 1, so minus 1. Okay, and this is what? Minus 10 and a minus 3. So it looks like we're going to have 13. It's not feeling good here, is it? And a minus 1 squared is just 1, and minus 1 plus 3 is 2, squared is 4. So it looks like we're looking at 13/4. Oops, don't lose the minus sign. For K1, K2 was minus 1.5. Okay, just in case we need to know, this is what, 3.25? In case they go that route. All right. All right, take a deep breath. That's those. Now all we have to do is extract K3 and K4. These ought to be a piece of cake. All right, for K3. K3 is S G of S evaluated at 0 is equal to K3. So that's going to be, just you can, S cubed plus 2S plus 6 all over S plus 1 squared times S plus 3. I'm really writing out all the steps here for this, but you'll be able to do these much faster when you recognize, oh, 0, most of these terms are going to go away, right? So I've got 0, 0, so this looks like 6 over, hopefully we won't get a 0 in the denominator. That's a 1, and that's a 3. So 1 squared is 1, 6 divided by 3. So we got a positive 2 there. Okay, and finally, S plus 1, GS, evaluated at S equals, no, that can't be, S plus 4, S plus 3. I'm skipping all over. S plus 3, S plus 3. Okay, and so this is what? This is K4. And we got, if I just look at that, I've got S cubed plus 2S plus 6 over S times S plus 1 squared. So that's what? 3 cubed is 27. Watch our signs. Minus 3 times 2 is minus 6 plus 6 over minus 3. Let's see, minus 3 plus 1 is minus 2, so that's 4 times minus 3 looks like minus 12. Okay, so I'm seeing the odd number of 27/12. So this looks like 2 1/4 and a positive 1 at that. So now if I put all this together, I've got my f of t is what? K3, that's a delta function, so I've got 2 times the delta of t plus, I've got the e to the minus 2, so that's K4, so plus 2.25 e to the minus 3t. All right, and then I've got, looks like I've got minus 1.5. Yeah, minus 1.5. And we've got minus 1.5. Now, what was K2 over? Oh, that's the S plus 1 squared. So, you know, what is that going to be? 1 over So that's our, well, we'll have to look that up in the table, right? And s plus 1, the quantity squared, that's like an s plus a, the quantity squared. That's going to be our t e to the minus t in this case. And then we've got the 2. No, not 2.25. We've got, where is it? Here it is over here. Minus 3.25. E, so this is on K1, e to the minus t. Okay, and all of these, just so we're reminded, since we've got a delta function in here, all of these turn on according to the unit step function. Okay, let's do one last one. And it will be this. I took this one from the 5th edition, so we got 60 over s plus 1. So here we're going to get to try yet another technique. And again, there are multiple ways to solve these, right? So we're going to write GS as a, let's just extract our a over s plus 1. So we've got a simple pole there. And then we've got a complex pole, right? So we'll write this as bs plus c, as the text suggests, over our s squared plus 4s plus 13. Okay, now we just have to find some way to solve these. First of all, let's get the a. This will only help us get s plus 1 times g. As I hope you've seen, even if there are repeated poles and complex poles, you can go pick off the easy ones with this, term elimination in the fractional expansion. So let's do this. We're going to do this at s equals minus 1. And so we know this is going to give us a. And so that will be 60 over s squared plus 4s plus 13. Okay, and if we evaluate that at minus 1, we're going to find out that a equals, we've got 60 over 1 minus 4 plus 13. So that looks like 60 divided by 10. So a is going to be 6. All right, now we need to get b and c. For b and c, all right, pick two values, two easy values of s that are not poles. Okay, and I'll pick 0 and 1, same one the text likes to use. And it's nice because those are easy. They're going to lead to easy arithmetic. So for s equals 0, right, what do we get? Plug this in, we'll get g of s. So now I'm back to this formula right here. And I'm just going to plug in s equals 0. So that'll be 60 over s plus 1 is 1 times s squared, 0, 4s, 0, 13. So 16 divided by 13 is equal to what? A over 0 plus 1, so that's a over 1. Kind of getting the idea why we did that. Now if s is 0, bs is 0, so this will be c over s squared is 0, 4s is 0, 13. Right? So canceling the 13s, this says a. Let's solve for a. Therefore, a is equal to 60 divided by 13. I'm sorry, I want I want C here. I'm not even going to dig up the eraser. We already have A as 6. So we have 60 over 13 is equal to 6 plus C over 13. And that means C is equal to, multiply through by 13, 60 minus 6 times 6 times 13. All right, 6 times 13 is 78, so this will be minus 18. All right, so if we got that as minus 18, let's try again for s equals 1. And now we'll have 60 over 2 times 18 is equal to what? A over s plus 1, so that's A over 2 plus B times 1, B plus C over, if s is 1, s squared is 1, plus 4s, 4 plus 13. So 13, 14, 18. So this is A over 2 plus B plus C over 18. Now we know C is minus 18 and A is 6, right? So we can plug in some numbers here. 6 divided by 2 is 3, and we'll separate this, B over 18, and C over 18 is minus 18 over 18 minus 1. And all of that is going to equal, what's this on this side? 30 divided by 18. Hopefully these are good numbers. Let's see. I can take a 6 out of here and make 5, a 6 out of here and make 3. And let's see. So this will be, I don't need equal. What I'm going to have is 5/3 plus 1 minus 3 is equal to B over 18. So let's see, 1 minus 3, so that's minus 2. That's minus 6/3 plus 5/3. So this is going to be minus 1/3 equals B over 18. So it looks like B is equal to minus 6. Okay, so this looks like the way we're headed here. Let's now put together the function. Right, we got all these pieces, but remember, here we are with this breakdown. We got this and these terms. Let's see what we got going on then. So we can simply break it up right away. Whoops, I'll get down here where the pen is. And we have A, which is 6. So what have we got? We've got G of t is equal to A 6 e to the minus t. Got that one easily enough. Now we have our BS over, so that'll be minus 6 minus 6. Oh, so let's see. We've got, let me look at this. We've got B will be minus 6 over, how can we factor this? Maybe s plus 2, the quantity squared. So that'd be 4, and then we got this 13 left over. So what's that going to be? Plus 9. So that would be plus 3 squared. Okay, so if omega was 3, And then this will be an offset, a delay. What have we got? We have 6. Let's see, what I really need here. What I really need is an s plus 2, right? I need this omega, or I need this s over s squared plus omega squared to give my shape. So I've got the 6s. Oh, I could borrow 2 from the c. I could borrow 12 from the c, right? So this would give me minus 6 e to the minus 2t cosine 3t. Okay, you see all that? So this worked out. I had 6s. This thing is equal to minus 6s minus 12. So I'm going to have to go up here to c. Where am I at? C is minus 18. So I'm going to have to rewrite the last term. This whole thing is going to become minus 6s plus 2 over s plus 2, the quantity squared, plus 3 squared. Okay, but then I've got 6 left over because I had minus 18. So it'll be minus 6 over, same thing, s plus 2, the quantity squared, plus 3 squared. So what have we got? This is looking a lot like the cosine, which we got, cosine of 3t. And this, boy, if I break this into 2 times 3, this is omega. Right? So this whole thing is looking like the sine of 3t. So I think we have it now. I go back down here. I've pulled this out. Where is my pen? All right, so now I've got, with my leftover, I've got minus 2 sine of 3t. But this is, don't lose this guy. Okay? So this didn't quite get added in there, but so this gets added into this. So here, I'll put it together here. 6 e to the minus 2t cosine 3t minus 2 e to the minus 2t sine 3t. All right, and this whole thing, as usual, is times the step function. So a little all over the page, but we got it there, and that's clear. So combination of ideas. Okay, plenty of problems for you to work through. I encourage you to work through those, plus your examples in the text, because all of the different techniques are used in